Ramanujan for G is now available on the Google Play Store. Try it out for free.
So hi students, so today we will continue with our explanation. Firstly, my happy Navratri wishes to everyone. So today we will continue with our description of what happens with diffraction. So I'm going to start there, but then I'm going to go on to further into optics, and then open up optics to a little further. As I explained before, we are looking to do all of optics in class 11 with the and then look to also integrate with the what we do with in class 12. Otherwise what happens is there's so much happening in class 12. But the previous time, that's what we did. We did the optics after electromagnetics. Anyway, so we looked at Young's double slit experiment last time, and we looked at the conditions for bright and dark fringes. So as we discussed, Young's double slit experiment deals with this idea called diffraction. So now what is diffraction? Diffraction is like this. If you have it is based on the wave aspect of light. It discusses how light, if it was a particle, purely a particle, it would just go in straight lines, right? Absolute straight lines, right? But then, the thing with light is that it is actually a more of a wave than a particle, and as a result, associated with a its wave behavior, you have this Young's double slit experiment, which then looks at the ways by which coherent light, so let me take a step back and discuss these various forms of light. We already discussed it a little bit last week. We discussed the breaking of the color of the natural sunlight into its various colors, right? So now we are going to discuss. So basically, light comes in, can be thought of as coming in packets, okay, and packets emitted by various different types of molecules far away in the sun. Okay, these packets, they come together, and then when you see it, you see this light in a certain color. It is said that certain and different animals see different kinds of light. There are some which only see black and white, and there are some which see only some colors. And of course, there are some which have very good eyesight. And of course, there are we already we discussed sound. There are some animals which have very good hearing. But the eyesight of, say, the eagle, right? The eagle has very good eyesight. But humans have this very good understanding of color. We are endowed with that. Of course, most humans. Some humans, struggle with seeing certain parts of the bandwidth. They'll find, I don't see blue and green that well. So and why I'm discussing this is so you understand that light is constituent. The light from the sun is a constituent of many colors. So that's part of what we are looking at. In the previous class when we looked at dispersion. Dispersion is the process by which you take light and you break it up into its constituents. That is natural light. Now this time we are going to but post that dispersion, we then went to diffraction. Okay? Diffraction is like this. It's a very different idea. Diffraction is like this: light which is produced by a coherent source. Okay, A coherent source largely produces light of one wavelength. Okay, so a coherent source which produces light, of one wavelength, then what we do is we take this coherent source, like typically a coherent source, it is generated. Light has to be generated by something like the laser, right? Light amplification by stimulated emission of radiation, laser, right? Laser is a material that when there is a certain kind of electricity pass through, it emits a particular kind of light. Okay, now the reverse of this is what we call as photoelectric effect. We'll come to photoelectric effect also next. But laser, what it does is it will emit light of a particular wavelength. Okay, and this wavelength, typically what we do is we pass it through, we kind of make this light float parallel, and then we pass it through a opaque, an opaque curtain or a wall, and in that opaque, like maybe a cardboard or whatever, and in that we make two small slits, and it's called Young's double slit experiment. And what Young's double slit experiment helps us to understand the wave theory of light. And so there is a screen on the other side of the of this cardboard with the two slits. And on that screen, what Young saw, were bands, bright and black. Okay, bright band, black band, bright band, black band, bright band, black band. And why did he see these bands, bright band, black band, with a certain thickness? And so the thickness associated with the with the bands that he saw, and those thickness varied with the laser. Why were those thicknesses changing, etc., right? And what are they proportionate to? Right? You do all these experiments in science, and they teach you a lot. Okay, a screen or a photo detector is placed at a large distance away from the slits. So you have the two slits, then a large distance away you have the screen, right, or photo detector. The laser emits, the light, and it's we have parallel light coming to these points. Really, the big picture here is that light is a wave, and there are quantums of waves which we see as constituent light, which we see as coming together into our eyes, and as yellow light, and then when it gets broken up, which is what happens in dispersion, right? It then breaks up. But the light emitted by a laser, on the other hand, is a coherent source. The waves are coming like that, in phase. So this is coherence, means wavelength and phase. So this coherent source light shows up here, and then it goes and hits this what is called the screen, right? Photo detector goes and hits the photo detector, and in the screen you see bands of bright and dark. Okay? So now, when do you see a bright band, right? You see a bright band when the difference between the lengths L1 and L2 is a number of wavelengths. Okay, so now at this angle theta, right? This makes an angle theta with the normal. So at this angle theta, how far does the light have to travel? Light has to travel d. D is the distance between these two, not d, right? D sine theta is what? d sine theta is the distance traveled, right? D divided by L is sine theta. So d sine theta, d divided by L is sine theta, right? No, no. So d uh, d divided by L, L is the distance traveled, right? So d divided by L is actually cos theta. Okay. So now what we can say is that so d divided by L is cos theta. So now there is a difference between the two L's. Okay. What is that difference between the two L's? The difference between the two L's is the change is this distance called delta L. Okay. Now, how much is delta L? Right? If this angle is theta, capital D divided by L, L1 is of course cos theta, right? Now this distance, this angle theta, right? This angle theta is also this angle theta. Okay, and if you said that this is D, right? Now D is again the is now the little d is the distance between the slits. Okay. Now little d, remember there is a big D, which is the distance between the slit plane and the photodetector, capital D. Small d is the distance between the two slits. So small d equals, right, or delta L equals, delta L is the difference between L2 and L1. Okay. Delta L equals small d sine theta. Small d is the hypotenuse. Delta L is the opposite side, right? So delta L divided by d equals sine theta. Okay. So delta L equals d sine theta. Okay. So, and this d is the distance between the slits. Okay. So now you have this monochromatic light source going through these double slits, and it hits this point, right? Now, when delta L is a certain number of wavelengths, n times lambda, you will see that it is additive, right? So that is the picture here, So if it is a certain number of times lambda, it is additive. Okay, if it is certain number of times plus half lambda, it is destructive. Okay, so then at those distances, the lengths will cancel, the lights will cancel, and you will have a dark spot. Okay, so and then in between there'll be a little bit of gradation, but largely that's the main point. So n lambda is a bright fringe, n plus half lambda is a dark fringe. That's the main thing you need to know here, in terms of the distance, Now, so now, if S is slightly off axis, then things get a little trickier. So you must then readjust it so that they come into phase. There will be a phase difference if S is slightly off axis. So you must try to make sure that it is exactly in phase. So then, it has to be right exactly in between. There has to be these two have to be exactly in between the two slits. So that is a very critical point also. If S is off axis, then there is a phase difference. The zeroth order bright fringe will not appear at O. Okay, so the zeroth order is when it goes like this and then it goes like that. Okay, so the zeroth order bright fringe is exactly at the middle of the line joining the midpoint of the slit and the source. So if you just extend that line, you will get the zeroth order bright fringe. And there, if there is a phase difference, it won't show up exactly there. So that's a very critical point. So there is a small it instead shows up at O prime. Position of the zeroth order maxima of the central fringe will be shifted. The condition for maxima, it will then become delta equals k times R2 minus R1 plus delta phi, and therefore the path difference is this. Okay, so this is a very tricky idea, and you should learn this also. Under what circumstances you get a path difference, and what is that path difference? So you have k times R2 minus R1 plus delta phi equals n times 2 pi. Okay, now so that is the path difference. Now the fringe width. What is the fringe width? The fringe width is the so now he is now looking at the fringe width when the um, when you have a shift. And what he's saying is the fringe width does not change regardless of when you have a shift. So you still get the whole thing will be moved. It will be moved a little bit this way, that way. So now for the nth fringe, if delta phi is a constant, the path difference R2 minus R1, R2 and R1 are the distances, and therefore the condition for the maxima is when k times R2 minus R1 plus delta phi is equal to n times 2 pi. Okay, so that is the main thing, and the path difference is n lambda minus delta phi by 2 pi times lambda. Right now, when they are perfectly in sync, this term goes away. Remember that this term goes away, right? So you then end up with this condition, R2 minus R1 equals n lambda, right? So now if there is a delta, right, then if there is a delta, which is the result of this, if there is a delta phi, right, then you end up with that shift having that added delta phi. Therefore that delta phi should produce you something as n times 2 pi. Okay, so therefore the path difference will have this added term n lambda, or R2 minus R1 have n lambda minus this. Okay, and this is the phi divided by 2 pi, and therefore that is the important idea. So now what is the fringe width? The fringe width is d by d times lambda, and what is d by d times lambda? Okay, the capital D is the length, the little d is the distance between the slits, and the fringe width relates these two. Okay, so now if you change the light, you will get you change the light source, you put a different laser there, exactly same point, then you will get this new d by d times lambda. Okay, so so that is the important idea there. So where the path difference is this, so the path difference is based on this other term. Okay, and therefore the fringe. What is this fringe width? Fringe width is the distance between the bright fringes. Okay, so the n plus 1 fringe and the nth fringe, right? The distance between the n plus 1 fringe and the nth fringe, that distance is d by d times lambda. Okay, so keep that in mind. That is an important fact you must remember for Young's double slit experiment. And the fringe shift is also proportional to the fringe width. So the delta phi and the level of shift that the fringe shift is. So if where is the fringe shift? Right. So delta phi by 2 pi times beta will give you the fringe shift. Okay. So now delta xn is correspondingly delta phi by 2 pi times lambda d over d. Okay, so delta phi by 2 pi, beta will give you the fringe shift, delta phi by 2 pi. times beta will give you the shift in the fringe. Okay, so if you got the fringe shift, you can then calculate the delta phi also, the phase difference. Okay, so now when the sources are off axis, you will get the corresponding shift in the in the whole position, and using similar triangles, you can determine if you had this much of a distance and you were this much offset, so L by L times D will give you X prime by D. Okay, so that's a very simple what is that, similar triangles equation. Okay, so L by L is the level to which you shifted the source, and the shift in the fringe will correspondingly be shifted that much. Okay, so so it is, the D's will cancel out and you'll have X prime by D, by capital D, right? X prime is the level to which this is shifted by capital D, will give you the ratio of, is proportional to the ratio little L by L. How much you shifted here is how much you will shift there also. Your fringe shift will also be corresponding. Okay, and so that should be quite obvious to you. So delta X by L will equal D by L, right? So that should also be pretty obvious, just an offset. So ratio, similar triangles ratio, right? So now fringe shift will also occur. The aperture plates QQ prime is offset with respect to SO. So this type of fringe shift is called lateral shift. Okay? So now we've discussed the fringe shift, constant phase difference, and we've also explained what happens with a coherent wave in the context of what happens with the Young's double slit. So the delta L, as we explained, delta L, if it is n wavelengths, right? If the path difference is n wavelengths, you will have a bright fringe. If it is n plus half wavelengths, you will have a pure dark shift, and in between will be small variations, right? So now if there is some variation in the delta phi, then things can change. So waves with a constant delta phi then are called coherent waves. Okay? So this is the interference between between two different lambdas. If you have more than one frequency being emitted by the source, more than one wavelength being emitted by the source, then you will have some amount of difference, interference with a source which emits multiple wavelengths. So if you had three wavelengths, blue, green, and orange, then the blue will interfere with blue, the green will interfere with green, and the orange will interfere with orange, because they are, that's how it is, right? Basically, you have multiple, the laser having multiple source wavelengths, and then these wavelengths will only interfere with each other. So you have if you had a 400, a 500, and a 600, the 400s will have their own beta, the 500s will have their own beta, and the 600s will have their own beta, right? And you will have a corresponding ratio, right? So and therefore the interference will be separate and between the various types of wavelengths, right? So they don't. So white light's interference pattern, right? You will have kind of, so if you used white light instead of, you will have a central bright at the meeting point, and then you will have the various other darkish minima, bluish minima, because you have a superposition of multiple colors, right? So what you will see is, you will see darkish minima, then you have bluish minima, reddish minima, etc., etc., etc. Okay, so at the center, of course, you will see the continuous bright maxima, because there all the wavelengths have traveled the same distance and they all hit the same, and you have a nice bright light at the center, right? So that's what it should be. The central fringe can easily be identified, and the fringe shift due to a phase change can be measured accurately using white light interference. Okay, so this is the thing with Young's double slit. A lot of involved ideas in Young's double slit. But the main geometry, please understand, and that's the one that matters. D by D times lambda. Remember that, and the beta. You remember the fringe width. How to calculate the fringe width, and then the fringe shift, right? So the fringe width d by d times lambda. The what happens in where do you get the n? If it is n lambdas, the path difference is n lambdas, then you get a bright, and then where will be the next one? It will be n plus half lambda. You'll get the next dark one. So remember those light and dark ones. Then remember the geometry. So once we've done Young's double slit, my suggestion is that you go and take a look at some bunch of problems, because now we have to move on. We have a lot of material to cover. So, I will quickly move on to the simpler parts of light, which is, we'll start with refraction, then we'll go back to reflection. Reflection is, of course, even simpler, but again, a subject, the difficulty of answering a question in a subject is not proportional to the ease of the subject. Okay, you must understand tough subjects, understand easy subjects also. Okay, so now I'm going to go to refraction of light. So again, see, when you look at our app, right, whether it is Sushruta or NEET, you will also get the actual YouTube there, from where the slides are made. So, and that will be included in the app. So you can look at the slides, but you also should look at the YouTube. That's very, very critical. Only then you will understand the material very, very well. Okay. So now let's look at Snell's law. Snell's law states that when you have two media 2 and media 1, right? Now, and let's say one of the media is air. Air has a refractive index of 1, right? And then the other is glass, typically refractive index around 1.5, right? But as we said yesterday, it varies with color in certain cases. That's what produces your the variance of refraction of the refractive index, then produces your difference, will produce your multiple colors, right? So now sin I by sin R is n21, where n21 is n2 divided by n1, right? So sin I is the incident angle, I is the incident angle, the sine of the incident angle, it then gets refracted. The sin R will be less, right? So in a higher refractive medium, right? So sin I by sin R equals n2 by n1, right? So now if one of them is air, the other is glass, right? Then n1 is 1, right? Now if one of them is something different, like maybe water, or it's some other kind of glass, right? You will end up with a different number, right? So so now glass, typically they use 1.5 for the refractive index of glass, but again, as I said, it varies between based on the wavelength, So sin I by sin R, and wave changes with glass also a little bit. Some glasses slightly different. Okay? So sin I by sin R, n21. Okay. So now when you go through a glass slab, right, what happens? The angle theta1 will, because Snell's law, applies both ways, right? The angle theta1 will equal the angle theta3, and the angle theta2 will be the same here. Theta2 equals theta2, right? So that you should expect, right? This one, theta1 will equal theta3. Therefore, sin I by sin R will be applied twice, and therefore, when it hits, it deviates, and then when it goes out without deviating. Okay, so because of that, you will not see, no angular deviation, but you will see a lateral shift in the ray. Okay, so that's what happens to the ray, and that's what happens as it changes medium. First and last medium are the same, then there is no deviation. right? So if you had multiple mediums in the middle, refraction through multi-layer structure, this one and this one are the same. So then you will end up with theta 1 and theta 6 being same. So this medium and this medium N2 and N5 are the same. Therefore, the the angles will appear the same. Okay, first medium and the last medium are the same, and there is no deviation. Okay, and emergence angle does not depend on thickness and refractive index of the layers. Thickness of each layer does not matter. All right. So now we will introduce this other idea, which is called total internal reflection. Right. So when some rays, will reflect. Okay, the incident ray and refracted ray and the reflected ray all lie in the same plane. Okay, and now the reflected ray will of course form this angle theta I and theta R reflected ray, where it will be the same if it is when it is reflected. If it falls at this angle, it will reflect at that angle. This angle equals that angle. This angle equals that angle for reflection, right? Refraction, there is a change in angle, sin I by sin R comes into play, right? So now what you do see is now under certain circumstances, you have a perception that something is not at, you see it as closer, right? So the apparent depth from the surface where the refracted rays appear, right? So you have a glass underneath, then you have reflection, you have refraction, and then reflection back. So what you do see is, at the end of the day, you have an apparent depth which is much less than the real depth with respect to what the eye sees. So the difference from the depth where the refracted rays actually meet, that is the real depth. So D versus D, what is the ratio, right? The ratio of D versus actual versus apparent is also the refractive index of the medium. Okay, so apparent depth by actual depth is also the refractive index in this kind of a situation. So this is the next idea that is taught. Now, when we look at the sun, right, due to the refraction of rays from the sun by the Earth's atmosphere, and of course the Earth, has various types of material in its atmosphere. Therefore it gives a slight bend. In free space you have n equals 1. Refractive index of free space is 1, but refractive index of atmosphere is a little bit more. It's not exactly 1. Okay, therefore what happens is, when you see the sun, it appears even after it has gone below the horizon, you can briefly see the sun. Due to the refraction of rays from the sun by the Earth's atmosphere, sun appears to be above the horizon before it actually rises. Sounds like a scene right out of the Mahabharata. So but I would like you to remember the idea as well, that the Earth's atmosphere has a refractive index slightly greater than 1. Okay? So this is as far as the first part of the discussion on refractive index goes. So now I'm going to go to the next set of discussions on refractive index. On refraction optics. So okay, so we first looked at sin by sin and refraction at spherical surfaces. So now you're at refraction of plane surfaces. Now we're going to look at refraction in the context of a spherical surface, which is what you will get when you look at when we start looking at lenses, right? A lens causes refraction, right? And then we will look at mirrors. When we look at reflection, we will also look at mirrors, right? Mirrors and lenses, they are pretty similar. Okay, so now if you had the incident light going from medium of whose what is that whose refractive index is n1 and a medium whose refractive index n2, which is greater than n1, then you will again have sin I by sin R happening, and and therefore you have to draw the normal. Think of a curved surface as a series of straight lines, each tangential. Okay, so you draw a tangent, draw a tangent, draw a tangent, draw a tangent. It's the same thing, because at that point it's the tangent represents the surface, and light is such a small thing, so just think of a lot of it as being a lot of tangents, right? So now the what then happens is, because of the variation, right? So you had this kind of a curved surface where there is a variation, therefore it is incident, and then it goes further away, then it and therefore correspondingly it will appear bigger or things will appear smaller, right? So and therefore you have this V by U. Notice the incident side is always U, the refracted side is always V, right? And therefore N2 by V minus N1 by U equals N2 minus N1 by R. So this is the real point that you should know. Sin I by sin R equals N2 by N1. You must know that. And this is in terms of the relation between the object distance and the image distance is related using this equation. Okay. N2 by V minus N1 by U equals N2 minus N1 by R. So please note this, and please try to do some problems involving this also. Okay. So now, typically, one thing that they often do is reflected light can be minimized by using anti-reflection coating. So when do you have that? Why do you have that? Why do you have reflected light minimization of reflected light, right? Sometimes you want to absorb as much light as you can, and sometimes you don't want to absorb any light at all. Okay? So like for instance, there are all these windows, right? Where these tinted windows, certain types of tinted windows, you can never see the hero inside his car, right? The hero is going in his Mercedes from Bollywood to Pune, for a party. Nobody knows. Why is that? Because the hero doesn't want to be seen. So for that they will use a different type of tinting of the glass. Okay, very true. Also, like privacy of inside a home, right? So if you get into construction, you will have to think about all these ideas, right? Anyway, so now when you have this instant angle small, what we then do is we look at how these, when you have very small angles, right? When you have very small angles, as you know, tan theta equals sine theta, right? Sine and cos theta is, when theta is very small, cos theta is 1. Sine theta is equal to theta, and also equal to almost close to tan theta. Okay, so now when these angles are small, then your I and R, sine theta will equal theta. Therefore, N1I will equal N2R. Okay, therefore, for small I and R, sine theta is approximately equal to theta. Therefore, now when you do the calculation, you can just use these small distance measures, right? For these two angles, alpha equals MD by OD. Okay, and the other one, R equals MD by DI. MD by ID, like, right? So using that, you can do the corresponding calculation, right? So MD by OP plus MD by CP, right? MD by OP plus MD by CP equals I. Okay, and and correspondingly R equals MD by CP minus MD by IP, and so using that, he goes on to calculate this, or more simply this equation, N2 by V minus N1 by U equals N2 minus N1 by R. Okay. Now, refraction by a lens. In a lens, there are two sides to the lens. There is this side, and then there is that side. So now, when you have a lens, when you have a thin lens, you then have these this equation changing slightly. What then happens is you will end up with this 1 by U plus 1 by V equals 1 by R, right? If you remember what happens to this N2 minus N1, right? So those equations will modify, and you will correspondingly have your resultant, equation 1 by F, right? Focal length equals N minus 1 times 1 by R1 minus 1 by R2, right? Which is called the 1 by V minus 1 by U equals 1 by F, right? So, so this is called the lens formula. 1 by V minus 1 by U equals 1 by F, and this is also derives from this formula, right? And so you have the principal focus, right? Principal focus is, like if you had, a lens like this, and then all the rays were coming, in parallel, they would all fall at this point called the principal focus, which is typically half the radius. Okay. Now, if you had radii being parallel, then you will end up with this principal focus. Okay. So now for a converging lens, F equals R times R by 2 times N minus 1. And in the case of glass, it is approximately R by 2. Right? Or so for biconcave lens, it is minus R by 2 times N minus 1. Right? Therefore, those are the equations for a convex lens, R by 2 times N minus 1. Okay. So if you had, the R's being equal, 1 by F equals 2 by R times N minus 1. So F equals R by 2 times N minus 1. Okay. So that's how the focal length is given, for various cases. Okay. So, so having discussed 1 by V minus 1 by U equals 1 by R, I am going to briefly also discuss total internal reflection, so that okay. So there is a angle, at which point, if as you keep, if you have you have the vertical, and then you keep increasing the incident angle, so there is an angle at which all the light is always returned. Okay. So now sine, if there is typically when you go from a rarer to a lighter, right, sine I will be greater than sine R, or I will be greater than R, right? Now, but when you go from a rarer from a denser to a rarer, right, you can end up with a situation right? When you go from a denser to a rarer, end up with a situation when all the light gets all the light incident at a certain angle gets completely reflected. Okay, now what is that angle? So now that angle is called the critical angle. Beyond that critical angle, all the light will get reflected. All the light which is incident at a certain angle will get reflected. That angle is called the critical angle. Therefore, it is the sine inverse of 1 by the critical angle is the sine of the 1 by n medium. Okay, so now go from this medium whose refractive index is n. The sine inverse of 1 by n medium will give you that critical angle. Okay, because now what we are saying is at that angle, right? This refracted angle will become 90 degrees. Okay? So sin I by sin r will apply, right? Therefore, it is you will find that for glass it is 1 sin I by sin r equals 1.5 by 1, right? And when you reverse, go from glass to air, sin I by sin r will become 1 by 1.5, right? So now you have what you do have instead now is sine inverse of 1 by 1.5. So sine inverse of 1 by 1.5 is some particular angle. You can look it up what exact angle that is, and therefore when the angle of incidence is greater than the critical angle, the entire ray will be reflected back. There is no refraction that takes place beyond that angle. Okay, so all the light is reflected back. Now reflection by the edges of a prism, you have total internal reflection. If you had this kind of a prism, right, and therefore you also have a retro reflector. If you have this kind of a prism, you will get all of the light getting totally internally reflected by that kind of a prism. It almost functions like a mirror. Okay, so this is now when we look. Having explained that, let's go to this idea of what is called an optical fiber. Okay, so typically, it is in optical fibers is a very important field today because there is so much data that gets transmitted through optical fibers. And typically what they do, they will have a source which they will have a laser, which will produce light at a fixed frequency. They will use this. It's part of the electronics of optics. And now the fiber itself will bend. Therefore you want the light to be able to reflect off that. Then they will. So what they typically do is they will have two types of. So there are two types of optical fibers. One type of optical fiber is called step index fiber. So there is an inner core which will have one particular refractive index, and there's an outer core which will have a different refractive index. This is the step index fiber. Okay. Then there is another type of fiber optics which involves what is called graded index fiber. And so today I think both are used. Typically it depends on it's a little the maths around. Of course you have to learn Maxwell's equations. They use mainly Maxwell's equation determining it. But roughly to explain this to you, what happens is it just bounces off the difference in the variation in the refractive index. Therefore, there is complete total internal reflection. So there is but then again there will be some little bit loss. So what they then do is they send the light, then it goes maybe distance. Then on the other side there will be a sensor which detects it. Then they will amplify it again. Then they will send it, and then there will be another laser which then sends it out. Okay. Then they try and keep that very much in with a small difference in sync. So there's there's a laser here which emits puts the light into this optic fiber, and then the fiber may bend and all that, and it will still go through all this and then reach the other end, and there will be another detector which will then detect it, then it will amplify it, and then put another piece of light on the other or into the next fiber in the daisy chain, right? So and so then they using this, they transmit data across amazing distances. There are all these undersea optic fiber cables today which transmit data between whole continents, and so today this is it can be considered among the great discoveries and received the Nobel Prize, and it changed, transformed, and helped facilitate what we today know as the internet, along with, of course, wireless technologies, right? So these two areas have been very central to our understanding of to the modern invention of electronics and the internet. So that's why I thought I will spend little time discussing this. Optical fibers are used in communication for multi-gigabit transmission. Optical fibers, they have sensors, and then they have lasers. The laser produces the high power source, and then there's the sensor. And of course, I should mention endoscopy. I've had a few endoscopies myself. What happens in endoscopy is they take a optical fiber with a small light, and then the gastroenterologist is the person who takes care of the largest part of your body, from your esophagus to your tummy. Okay, and what they do with the endoscopy is the first top half, they will put that light, and then they will go and look inside your body using most probably the esophageal up all the way up to the stomach. Okay, so that is how they have this fiber optics that goes in. Then with that, they will be able to see what's going on in there. Okay, so again, amazing technologies that come to serve humanity in its quest for a better life. Okay, so now let's move on to the mirage. Right, the mirage happens. You must have seen a lot of movies with that. So what you end up seeing is something which is much further away. So now here you have this person walking through plains or desert, walking. Suddenly he says, "Oh, there is water here." And actually, there is no water. Everybody thinks it's you're seeing things because you want to drink some water. Illusion of the presence of a reflective surface such as water on a hot sunny day due to variation in the refractive index of the atmosphere. That's what a mirage is. Now, the light from this tree, right? It should come. You should not be able to see it, but then it bounces and it comes off, and you do see it. Okay, so so that happens because the light bends, because closer to water you have a different refractive index versus elsewhere. So there is a bending of due to variation the refractive index, the atmosphere, between rare atmosphere where there is no water, and when there is little bit water vapor tends to have a small amount of refractive ability. Okay, now finally, I mentioned the graded index, graded refractive index. This is basically, if you have it's a type of glass whose refractive index varies with y. You see, as it goes up, right, the refractive index changes. Okay, so now Snell's law is applied successively, and there is a bending of it seems like there is a bending of light. So that is the other type of step index fiber we already discussed. You have N and N1 and N2. Here there is a gradation of the refractive index. This is called a graded index fiber, and therefore there is this graded index of the medium in between. So now light waves coming from a distant object curve as they reach the eye. Okay, So, I've run out of the 1 hour. Um, so now what I'm going to do is I'm going to ask all students, 11th class students who watched the last two classes to attempt all the questions that you can. Please attempt questions in these two subjects. One is Young's double slit experiment. Understand dispersion and Young's double slit experiment. Do a lot of problems there, and then do refraction. Okay, I will try to keep moving forward here because there's a lot of material here, and doing problems is typically required from the student side. Okay, we explain this with a view that the student will get the app and then they will attempt problems after learning the material. This is how this works. We try to move pretty fast through the material because we want students to be able to then learn at their own time, at their own pace, because I get 1 hour with you, right? And now you have to spend another 2 to 3 hours. You have to spend the time learning the material, then you have to spend time solving the problems, okay, and then you have to build your own comfort with the material. So it's a very different kind of learning where there's a lot of onus on the student. Okay, that's why we have our apps, Ramanujan and Sushruta. I strongly recommend, if you're a NEET student, that you get our Sushruta app. Go to play.google.com, com.jnanamarga.sushruta, and otherwise you go to you please download Ramanujan if you're a JEE student, com.jnanamarga.ramanujan, and download the correct app, install it on your Android compatible device, and then you're up and away. Learn the material, read the textbook. See, our material comes with 3 different: read the textbook, watch the video, look at the slides, listen to my lecture also, or Professor Tiwariji's lecture, or Dr. Bhatt's lecture, or Tarun's lecture. Then you take the next step, and then you do some problems. Then you come back to the material. See, if you get a question wrong, you go see the answer. Okay, then you come back and learn the material associated with that question in the book and in the videos and in the slides. So when you do that added diligence, so if I teach for 1 hour, you have to study for 3. When you provide that added diligence, your understanding improves. You would have learned the material better, and you will be able to answer more questions. So that is the key in teaching this material in such, and as you know, these exams, JEE and NEET, their aim is to provide a gradation in terms of the marks. So, and also when you study for CBSE, you learn from, learn the material well, and you will get very good marks if you learn the material. Now, if you are taking NEET, JEE, they look to build that gradation in the marks, and therefore you must learn correspondingly better than the next student. So that's very, very critical also. Okay, so please aim for that, and I will see you all again next week. And we will look to support you all through this whole process of taking these exams, readying yourself, and finding a place for yourself in the world in science. All right. Thank you very much.